So we were discussing the O3 group, and we were discussing O3 and SO3. Okay, so let me continue that discussion. So what is SO3? So one way of characterizing SO3 is the group of rotations in 3 dimensions. In 3-dimensional Euclidean space, okay? But it also is a subgroup. So SO3 is also a subgroup of O3. And I've claimed that, well, it's a definition that SO3 is the component of O3, for which all the determinants are +1, right? Because we saw that the definition of O3, the definition of O3 includes all matrices which satisfy, 3x3 matrices which satisfy the determinant of O squared to be 1, which also includes the, it includes, both determinant plus or minus 1, right? Cases. All right. So as an exercise, I would like to give you something to do, which is, show that the subset of O3, that consists of the matrices with determinant -1 do not form a group. Okay, it's a 2-line exercise, or 1 line, I should say. But it needs you have to think about it. Just 1 second, okay? So this is something I want you to do by yourself. Okay? All right. So let's get back to our main discussion. So we said that one way of characterizing SO3 is that it's all the element, it consists of all the elements of O3, which I should say that, that are not continuously connected to the identity. So here, the identity element of the matrix group, we identify with that to the identity element of the group. The two are the same. So for matrix groups, this is not a controversial thing. Okay? So what do I mean by that? Let me, since you like pictures so much, so suppose this is O3. O3 has essentially 2 components. So 2 disjoint components in terms of continuity. Let me make this a little further. Okay, and one of the components, it corresponds to all the determinants equal to +1, and all the determinants of matrices equal to -1. And the identity element is in the +1 component. So this is essentially what we are calling SO3, this component of O3. So any element in SO3 can be continuously reached by some change of parameters from the identity element. Okay, so
Sir, will there be a not in the statement above? I just got confused. Like the line you wrote before this.
SO3
Not
consists of.
continuously. It should be. Should it be a not?
Sorry, yeah, thank you so much. Yeah, I don't know where this not is very naughty. Yes. Okay, connected. Thank you very much, Mahi. Yeah. All right. Yeah. Thank you so much. Yeah, I'm very sorry about that. So, whereas, to go to the disconnected component of O3, well, disconnected to the identity, that is, you have to apply what we have been calling P, the parity matrix, okay, which is also, P is also in O3, but all the elements over here, they are not connected to the identity, okay? So if we apply, for example, the element corresponding to the identity after we apply P is P itself, right? Okay, so this is the geometrical picture of SO3, which is sitting inside O3. Okay, so physically, this means that, any rotation in 3D can be built up from an infinite number of, say, infinitesimal rotations. Okay. So it's just a usual, physical idea we have of motion or, translation. Okay. So we want to actually show this. I think it's a good conceptual exercise. And before we show this, let me introduce a definition. Okay. So the definition of generators, okay, or generators of a continuous group. We will call these groups Lie groups eventually, but let's just stick to continuous groups for now. Okay, so let G be a continuous group let's say continuous matrix group of dimension D. Now, with each element say small g, parameterize, let's put a theta here, theta vector, parameterized by say theta, which is a vector, which has n component, sorry, d component, by which are d real parameters, okay? So we are making the d real parameters into a d-dimensional vector, okay? Now, if we look at G delta theta, that is a group element, infinitesimally close to the identity, and write it as G delta theta as the identity matrix plus delta theta dot of x. What is the dot means? This means that delta theta dot of x is delta theta I xi, right? So it should be clear that, so I'm using the Einstein summation convention. So therefore I'm not writing that there is a sum over I which goes from 1 to d, okay? That's implied because we are repeating the index. And it should be clear that xi are matrices, okay?
Sir,
Yeah.
what does it mean for two matrices to be close to each other?
Yeah, that's a very good question. Informally, it means that these parameters are very small. So that if I choose this whole matrix, this is a very informal way of defining it. You can do it formal. You can do a formal version of it. You can say, so this is a matrix, right? That all the elements of this matrix are very small numbers.
I see. Okay.
Okay. So I mean, you can make it more formal. Like you can
define a norm here. Like,
yeah, you can define a matrix norm, but it just becomes very heavy-handed for my taste. So okay, but you can define all of those. Yeah, you can define a norm for matrices. Okay. Okay, so we see that there are xi matrices, right? So if you write the infinitesimal element in this form, then the D matrices given by x1, x2, dot, 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 x of D are called the generators, okay, of the group G. Okay. Is this clear? So, if you think of the group, if you look at the parameter space, so it's some manifold, then there is the identity here, and each of these parameters, say theta 1, theta 2, they are telling you how far you can go in each direction. But that direction is parameterized by x1. The theta is the parameter, but the tangent vector in that direction are represented by x1, x2, etc. Okay, so from a geometrical point of view, the generators are nothing but tangent vectors at the element at the tangent plane at the identity. So this is basically using that. I'm just using the language of differential geometry. You don't have to know what a tangent vector is, okay? Geometric, like intuitively, if you have a curved space and you pick a point and you imagine a plane that touches that curved space just at that point locally, then the vectors that form the basis of that space are known as the tangent vectors. Okay, so is the definition of the generator clear, at least from an operational point of view? Okay.
So are the generators elements of G?
No, the generators are not elements of G.
Okay.
They are elements of what we will call the Lie algebra. Okay. Yeah, they are not elements of G. They are elements of the tangent, on the tangent space.